CITS Pre-Calc Section 2.2 is our Introduction to Functions. Now, functions is a big part of mathematics, okay, because everything that we do later on is we try and solve in terms of functions what happens, and we do a lot of general terms. This section isn't really bad. It's just getting us used to the concepts and the terms of functions. Okay, so we start out with our definitions as normal. Definitions, okay, our relation. A relation we know is a definition or defined as any set of ordered pairs. It's how they're matched together. So a relation is 2 goes to 3, okay, or -1 goes to 5. A relation goes between our x's and our y's, or in function notation, our f of x. Okay, so that's any relation, any set of ordered pairs is a relation. Now, a relation does not have to be a function. A function is defined as a set of ordered pairs in which no two ordered pairs have the same first coordinate and different second coordinates. We always say it, for every x there can only be one and only one y. Okay, so in this case, 2 has to only go to 3. -1 has to only go to 5. I can't also have 2 going to 4 and it being a function. Okay, it still can be ordered pairs, it can still be a relation, it just can't be a function. Okay, so every x goes to only one y. The domain of every function is basically just all the x values. Okay, it's a set of all the first coordinates of the ordered pairs. We always call it every possible x that we can plug into that relation. The range is everything that comes out of that function. Okay, so it's all the y values. So after I plug in all the possible x's, I get out all the y values for it, which makes all my ordered pairs. Okay, so domain is your x's, range is your y's. In the function given by the equation y equals mx plus b, we always call x, which is a variable, or the value being plugged in, as the independent variable. That's the one we plug in. Y depends, whatever I get out for y depends on what I put in for x. So therefore y is the dependent variable. So the x is independent, that's what goes in. The y is the dependent, that's what comes out. In function notation, and you've all seen it before, the y just changes the f of x, and we get the f of x equals mx plus b. If I were to look at f of 3 then, remember we just plugged that number in for the x, and we can solve out and find our y value. Now, to determine domain and range, which is going to be a big part of this section, to determine the domain of a function, it's a lot easier to make an assumption and then find something else. So it's easier to assume that the x is all real numbers, which we can write a couple of different ways. I prefer this way. Okay, so all real numbers means that I can plug in any x into it. Then find out what you can't plug into it and take that out. Okay, so we'll have a couple of examples, but we know that I can't divide by 0. So if I've got a function, say 1 over x minus 3, I assume that the domain is all real numbers, but I know that x can't equal 3 because I would divide by 0. So therefore there's a break in this function, or in this domain, and I can only go all the negative numbers up to 3, and then I start again at 3 and go all the positive numbers. Again, the open brackets point out that I can't have 3. So this is a set notation on how to write it. Okay, so we're only looking for things that can't go in. Now, we do have one more function to define here. It's called a piecewise function. A piecewise function happens because we can't always define what's happening with just one function or one statement. So what we have to do is we'll end up changing, and depending on the values of x being plugged in, it might be defined differently. Now the graphs of these look a little bit strange, okay? But we can kind of walk through this here. Basically what this tells us, if x is always less than -2, so for any negative number less than -2, the domain is defined by the linear function 2x plus 1. Okay, so how I graph that is I plug in the -2 here, and I get -4 plus 1 is -3. So over at -2, down at -3, I have a value. but it's not an equal value because there's no equal sign, so it's an open graph. I then look at how I would graph this function. Well, 2x plus 1 is a positive slope, so technically I would have a line going up through here, but I only use the negative values. I only have that line going down low. So that graphs the first part. The second part, x squared minus 1, only happens between negative 2 and positive 3. So at negative 2, I can plug this value in. Negative 2 gives me a positive 3, so at negative 2, I'm up at 3. Now, that's a closed circle because it's an equal sign. I can plot the rest of the points. I put in negative 1. Okay, negative 1, I get 1 minus 1, I get 0. At 0, I get negative 1. At 1, I get 0. At 2, I get 3. And at 3, I get 8. So I'm up here somewhere. And all these are equal signs, so they're solid dots. So there's the graph of the second part of the function. The third one goes back to a linear. Any number bigger than 3, I use 4 minus x. So if the value is 3, I end up with 1. So at 1, 2, 3, I'm up here at 1. And that should again be an open circle. Okay? And I have a slope of negative 1. So over 1, down 1, over 1, down 1. This graph's going to look like that. So there's the graph of a piecewise function. So depending on what value of x, you're looking at a different function to plug into to find the value. Okay? Now I've got a few more notes. X-intercepts of a function. Again, and we've heard this before, I've talked about it in all classes. The x-intercepts, they have different ways of asking for it. You just have to know what they're asking for. The x-intercepts are also called the zeros of the function, the solutions, or the roots. They can ask for those intercepts in all three ways. We find them always the same way. We set the equation equal to 0, and we solve it. Now we have a quick way to check graphically. I'm sure you all remember the vertical line test. Okay, vertical line test just says if I have a graph, and if I can draw an infinite number of vertical lines through it, and never hit the graph at more than 1 point for each line, then that value is a function. So our parabola here is a function. Okay, so we don't have to worry about too many y values for 1x. Now on this one, if I look at the vertical line test, right here I end up hitting it twice. So therefore, when x is, and we'll just say this value is 5, I could have 3 possible values for y. So therefore, this one is not a function. Excuse me. And the last one is a line. I think we'd all agree a line has to be a function. So a quick test if you have the graph. Vertical line test tells you if it is a function. We also have what's called the horizontal line test. The horizontal line test tells us if it's 1 to 1. Okay, 1 to 1 means that for every x there's only one y, but also for every y there is only one x. Okay, so therefore, if I look at these graphs again, the parabola, I do the horizontal line or the vertical line test to see if it's a function. I do the horizontal line test to see if it's 1 to 1. This one is 1 to 1. This graph, it's not a function, it's not 1 to 1. This one is a function, it is 1 to 1. Now, the question is for you, is a function always 1 to 1? No. A function is not always 1 to 1. Okay? If it's not a function, is it not 1 to 1? Not necessarily. Okay? There are some weird circumstances out there, but basically we worry more about the function and not the not function. So a function can be 1 to 1, it does not have to be not 1 to 1. Okay? For our rules, a function is 1 to 1 if and only if, and I'll start abbreviating it like this just so I don't have to write so much. A function is 1 to 1, this means if and only if the function evaluated at a equals the function evaluated at b, implies that a equals b. Okay, so if I solve one out, I'm going to get the same on both sides. A function is increasing, in other words, it's going up if when you plug in a value of a and a value of b, f of a is less than f of b when a is less than b. It's decreasing when you plug in an increasing value of a, the value goes down. And it's constant when you plug in a different value of b, the values are the same. Okay, so kind of read them a little bit backwards here. When I plug in different x's, increasing values of x, the values increase. That's an increasing function. When I plug in increasing values of b, or of x, it goes, if it's, I got a little bit screwed up there. They're equal. If I plug in equal values of x, the functions are equal. If I plug in increasing values of x and the function value increases, that's increasing. If I plug in increasing values of x and the value goes down, that's decreasing. If I plug in two different values of x and they're constant, that means the values are the same. That means it's a constant function. Okay, so I've got a few examples to go through. There's no way I'm going to get through them in the 8 minutes left that I have, so I'm going to stop this video and we'll have a second part with the examples.